I have good news about Section 3.6. What's the good news?
Easy?
I wouldn't say easy. You do not get to use your calculator for everything. The good news is there's nothing new.
Nothing new.
Nothing new. Section 3.6 is kind of a combination of the last three sections we've done. So I'm going to give you a function like y equals 3x over x squared minus 1. And I'm going to ask you a lot of questions. I might ask you, what's the domain? I might ask you, find all intercepts. Find all asymptotes. Classify all critical points. Determine increasing, decreasing. Determine concave up, concave down. Find all inflection points. And once you have all that wonderful information, draw me a very accurate graph.
It would be a combination of disjunctive, precalculus, algebra, and everything.
That's right. So this has basically 3 through 7 is all the stuff we very recently did in this class. Those are the last 3 sections. 1 and 2 are a combination of some pre-calc stuff. But not a whole lot. All right, so looking at this problem, you should pretty quickly be able to tell me what the domain is. What's the domain? Except and negative 1. So I would just write x cannot equal plus and minus 1. We cannot have 0 on bottom. Determine all intercepts. Well, if x equals 0, this will give me the y-intercept. If x equals 0, y is 0, which also happens to give me the x-intercept. In this case, there's only one intercept. That happens to be the origin, 0, 0. How would you, in general, find the y-intercept? Set y equal to 0. But if you set y equal to 0 for a fraction, the only way a fraction can be 0 is for the top to be 0. So x would have to be 0. So we only have one intercept here. Determine all asymptotes. What are the asymptotes? X equals plus or minus 1. That's the vertical asymptotes. The horizontal is y equals 0. Y is the horizontal asymptote, y equals 0. Well, I agreed that 3 times 0 equals 0, but that's not why y equals 0 is the horizontal asymptote. This is what we did yesterday. You look at your powers. When the power on bottom is bigger, the limit as x goes to infinity is always 0. So that tells you your horizontal asymptote is 0. All right, so that was the easy stuff. Now comes the harder stuff. Classify all critical points. What do I need to do to classify all critical points? I need Mr. Derivative. So y prime is bottom x squared minus 1 times the derivative of the top, that's 3, minus the top, 3x, times the derivative of the bottom, 2x, divided by bottom squared. If I simplify that, I'm going to have 3x squared minus 6x squared, so that's minus 3x squared minus 3. So I go to draw my number line. And I definitely know I want to mark negative 1 and positive 1 on my number line. Why do I want to mark negative 1 and positive 1 on my number line? That's where the derivative is undefined. And I also want to mark any points where the derivative equals 0. Where does the derivative equal 0? At 0? No, definitely not at 0. If I plug 0 in, I get negative 3 over 1. What's that? No real numbers. Correct. Why no real numbers? It will give me a real number. More importantly, it will not give me the special real number 0. When will I get 0 on top? Only when x is imaginary. That's correct. James, you get it. Simplify it? I could. I could write it as -3 times x squared plus 1 over x squared minus 1 squared.
Then you can't break down x squared minus 1.
I can break down x squared minus 1. Unfortunately, I cannot break down x squared plus 1. X squared minus 1 I could write as x minus 1x plus 1.
And then all that would be squared.
And then all that would be squared. That's correct. But none of that's going to reduce with x squared plus 1, unfortunately. But I do think it helps to write it that way because then I think it's even more clear that the top is never the number 0. So, classify all critical points. That's easy enough. There are none. Why are there none? Because I said so. Because the only places that we got were not in the domain. The only values we got from the first derivative were 1 and -1. They're not in the domain. All right, so I start picking my favorite numbers. Favorite number bigger than 1. 2. If I plug 2 in, I'm going to have 4 plus 1, that's 5. 5 times -3, that's going to be negative. And then the bottom is always going to be a positive thing, isn't it? Because it's got that square around it. So that's going to be negative there, isn't it? Favorite number between -1 and positive 1? 0. If I plug 0 in, I get 1 times -3. That's negative. The bottom is always positive. Negative divided by positive is negative still. And finally, my favorite number smaller than -1? 0 is not smaller than -1. How about -2? Plug -2 in, I get 4 plus 1, that's 5. 5 times -3 is negative. Negative divided by positive is still negative. That's unusual, but that can happen. We got decreasing everywhere, didn't we? That's unusual.
Like, decreasing everywhere, a certain way to reach that point, or?
Nope. It means this function is always decreasing. Except where? Except at the asymptotes. So let's just, at this point, draw a graph of this function and see if we think we're on the right track or see if we think we're nuts here. 3x divided by x squared minus 1.
It's an inverse absolute.
No, not really. But I do look at it and I see over here the function is decreasing. Then there was the asymptote. In this part in the middle, the function is decreasing. And then to the right of the second asymptote, the function is decreasing again. So I think we're correct so far. I think this function is decreasing everywhere. Except 1 and -1. Decreasing everywhere except x equals plus minus 1. That's where the asymptotes live. All right, we're almost done. Concave up, concave down. Got to find the second derivative, don't I? And that's where these problems get pretty ugly, finding the second derivatives. Y double prime is the bottom, x squared minus 1 squared, times the derivative of the top, -6x, minus the top, -3x squared minus 3, times the derivative of the bottom, chain rule, 2 times x squared minus 1 to the 1, times the derivative of the inside is 2x. All divided by the bottom squared, which is going to be x squared minus 1 to the 4th. All right, we've seen quite a few of these problems with rational expressions. Something should cancel. What cancels? X squared minus 1. There's an x squared minus 1 everywhere. So that one, and that one. So that power on bottom becomes a 3. Distribute, clean up, see what we have here. we have minus 6x cubed plus 6x. Minus and a minus is going to make that a plus. We've got a 3x squared times a 2 times a 2x. That's 12x cubed. And then again, I've got a minus and a minus. That's going to be a plus. I've got 3 times 2 times 2x. That's 12x over x squared minus 1 cubed. All right, so simplified. I think we have 6x cubed plus 18x over x squared minus 1 cubed. And I think I'll even go a step further. I think I'll write that as 6x times x squared plus 3 over x squared minus 1 cubed. Once again, if I were going to be mean and give this problem on a test, I would give you the first derivative, I would give you the second derivative. It would take too long and generate too many errors for me to expect you to do that under testing conditions. Okay? So once you have that second derivative, you should draw your number line. I mark down the number 1. I mark down the number -1. Are there any other numbers I should mark down? 0. Why 0? Because that makes 6x equal to 0 right there. X squared plus 3. When does x squared plus 3 equal 0? No real numbers. That's correct. So we do gain one new point here. One new x value, x equals 0. All right, we plug in our favorite numbers. Favorite number bigger than 1? 2. You plug it in, you can check it. It's positive. Can't give up. What's your favorite number between 0 and 1? 1/2. Plug in the half, work it out, check it. I think you'll get a negative number. Favorite numbers between 0 and -1? -1/2. If you plug -1/2 in, that's going to be negative, that's going to be positive. That one's going to be negative. So you'll get concave up there. And finally, favorite number smaller than -1? -2. You would get concave down. So you can go through the arithmetic there and make sure I didn't mess it up. Pretty confident.
That means that all 3 of those are, no, only 0.
Only 0 is an inflection point. Excellent. I'm glad you changed your mind in the middle of your sentence. How come 1 and -1 are not inflection points? They are not in the domain. So we have one inflection point, 0, 0. And the concave up, concave down, up would be x is between 0 and, or -1 and 0, and x is bigger than 1. And the down would be x is less than -1, and x is between 0 and 1. That's true. There, I wrote that. I wrote up when x is between -1 and 0 and x is bigger than 1. Down when x is less than -1 and x is between 0 and 1. Okay, now I'm ready to draw a graph. So here's my graph. I know that at x equals 1 and x equals -1, I have vertical asymptotes. So I draw my vertical asymptotes. Asymptotes are typically drawn as dotted lines. At 0, y equals 0, I have a horizontal asymptote. So I would draw dotted lines that way. And then the only point I have on the graph is the point 0, 0. All right, so what happens in between the two asymptotes? Between -1 and 1, the function is decreasing, isn't it? It's got to be coming down. But it switches from concave up to concave down. So I think it has to look like this. It has to be concave up. So it has to look like it's coming down and it looks like it's going to turn around, well, what happens? Does it turn around and go back up? No, it switches to be concave down. So that's kind of a tricky one there. It looks like it's going to turn around and go back up, but it doesn't. So it's concave up here, so it's got to curve that way, but then over here it's got to be concave down, it's got to curve that way. What happens when x is bigger than 1? It's still decreasing according to my derivative chart, but it's got to be concave up according to my second derivative chart. So how can the function be decreasing and concave up at the same time?
Asymptotes like this.
And it's got to get close to the asymptotes and be like that, I think, is the only choice. I think that's the only way it can be decreasing, get close to the asymptotes, and be concave up. And then conversely, when x is less than -1, it has to be decreasing, it has to be concave down, and it has to get close to the asymptotes. I think the only way it can be decreasing, concave down, and get close to the asymptotes is to look like that. Questions on that? On a quiz or on a test, I would generally give you a grid to use to draw that. Other questions on that? So what's happening here is I'm not giving you a formula to work with. I'm just giving you a bunch of information about the function. All right, so what's happening in part A for number 1? F at -3 equals 4, f at 2 equals -5, f at 0 equals -3, f at -5 equals 0. What's that? I'm giving you a bunch of points on the graph. All right, so we can draw those points right in. So I've got -3, +4. 2, -5. 0, -3. And -5, 0. So part A there, I just gave you 4 points on the graph. That's all that is. Part B. F prime at 2 equals 0. F prime at -3 is undefined. And F double prime at 5 equals 0. What's the difference between the derivative is 0 and the derivative is undefined? Okay, it means at -3, we could have an asymptote, but I don't think we do because I already gave you a dot there. Or there's a point missing, which that didn't happen because I gave you a dot there already. Not a jump. It might be a maximum, it might be a minimum. What's the difference between derivative is 0 and derivative is undefined? When the derivative is 0, you usually have a minimum or a maximum, but it's nice and smooth. What happens when the derivative is undefined? Quite often you have a cusp. You have a sharp point in the graph. So since I gave you the point -3, 4, I think what I'm telling you here is that there's a sharp point in the graph right there. That's what derivative as undefined should mean to you. Sharp point in the graph. F double prime at -5 equals 0. What's happening there? Probably going to be an inflection point. I won't know for sure until I know more about my second derivative. Okay, then it says f prime of x is greater than 0 when x is less than 3 and x is greater than 2. F prime of x is less than 0 when -3 is less than x is less than 2. What I like to do with that is I like to draw a number line because I'm used to dealing with this with a number line. So I'm going to mark down the important points they gave me. They're -3 and 2. And it told me the derivative was positive for x bigger than -3. So it's got to be increasing there. And the derivative is positive when x is bigger than 2. And finally, the derivative is negative in between. So part C gave me my increasing, decreasing information. Also gave me my minimum and maximum information, didn't it? All right. And then part D, I'm going to do kind of the same thing. I'm going to draw another number line for second derivative. And it says the only important number apparently is -5. The second derivative is for smaller than negative 5 and positive for bigger than negative 5. Okay, so from that information, from this increasing, decreasing chart, this concave up, concave down chart, the points that we have, we should be able to draw a very accurate graph. So what has to happen? Well, we know at negative 3 we have to have a what? A maximum. And we also know at negative 3 the derivative is undefined, which means we have a cusp. So we it's got to be when I'm smaller than negative 3, it's got to be increasing and concave up. So I think it has to look like this, close to negative 3. I think that's the only choice. At negative 3, there's got to be a sharp cusp. It's got to be increasing on this side, decreasing on that side, but it's got to be concave up all the time, doesn't it? So it stays concave up until what happens?
Until it reaches the negative 5, 0.
And then it changes to
Concave down.
concave down, so it kind of has to go like that. So the curvature there kind of has to change. Okay? From negative 3, 4 to 2, negative 5, what happens? It's got to be concave up, and it's got to be decreasing. And what happens when I get to 2? It has to start going back up. So I think this side has to look like this. It's got to be decreasing and concave up. When I get to 2, negative 5, it switches to be increasing and concave up. I think it has to go like that. All right, I'm out of time, so you get to go home and try number 2.